Alright, starting 3.2, they start out with something called Rolle's Theorem. And Rolle's Theorem is going to be used a little bit later to prove the mean value theorem, which is real important for later sections. So Rolle's Theorem requires that we have a continuous function f on some closed interval ab, and it needs to be differentiable on the interior, so the open interval ab. Then the other assumption we make is that the endpoints outputs are equal, so f of a is equal to f of b. And then the conclusion of Rolle's theorem is there exists a c in the open interval ab such that the derivative at c is 0. So we have some sort of horizontal tangent. So what we'll do when we start the proof is we'll suppose that we have some number d that's equal to f of a and f of b just for convenience. And we'll make sure we have the assumptions f is continuous on AB and on the closed interval AB and differentiable on the open interval AB. So there's two cases. One where the function's just constant the entire way. If it's constant, then the derivative of constant is 0, and we have what we want. The second case is where the function's not constant. So you're going to have some interior point that's either above or below d. So let's go ahead and take care of case 1. If f is constant on the closed interval AB, so we just said that, so f prime of x is going to equal 0 for all x in the closed interval AB. And that's exactly what we want. We got the conclusion there exists a c such that f prime of c is equal to 0. So we got what we wanted there. Second case is f is not constant on the closed interval AB. So there exists a c in AB such that f of c is greater than d. It could also be less than d, but the argument's very similar. So it could be less than d or greater than d. We'll go ahead and do the greater than d. The cases are very similar. By the intermediate value theorem, we know that because the function's continuous on the closed interval AB, it's going to achieve a maximum and a minimum, but we're going to focus on the maximum within the closed interval AB. Since f of c is greater than d, we have to have a maximum, because the maximum is not going to be at the endpoints, because this f of c is larger than the endpoints outputs. So the max is not at endpoint. So there exists, we'll just call it an x naught in AB such that f of x naught is the maximum of f on the closed interval AB. And since x naught is in the interior AB open interval, and we know that it's differentiable on the open interval AB, the derivative at x naught is going to be equal to 0, and that's from previous results where we proved it in section 3.1. If we were at a minimum or a maximum, we had a horizontal tangent. So we found this x naught. We have no idea where it is, but there is one. I've drawn in two graphs here. In yellow there, that would be the case 1 where we just have a constant function, so it's going to be the slope of the constant is 0, and when we take the derivative, that's going to give us the slope of the line there, and so it has slope 0. On the second one here, you see that the endpoints are equal, and then we have some c that's larger than d, and then we see that we have our x naught, and we have a horizontal tangent there. So that's what that theorem's guaranteeing. So this is just kind of a stepping stone theorem to get to the mean value theorem. There are some applications, though, so we're going to do a couple problems with some applications of Rolle's theorem. All right, continuing on, we'll do a couple examples of Rolle's theorem. Here we have f of x is equal to x squared plus 3x. And we're going to consider it on the closed interval -3 to 0. So this is going to be a parabola opening up, and if you remember the axis of symmetry, which is negative b over 2a, that is the formula for the x-coordinate of the vertex. So the x-coordinate of the vertex for this thing is negative 3 over 2, and that's where this thing is going to achieve a minimum. Coincidentally, that is within this interval here. So in order to use Rolle's theorem, it has to be continuous. Polynomials are continuous everywhere, and differentiable on the open interval, which it is. Polynomials are differentiable everywhere. And we got to check the endpoints. So we're going to plug in the two endpoints to make sure they are both equal to each other. It's not always the case that they're both going to be 0, but in this particular problem, they're both equal to 0. Okay, so I got continuous on the closed interval, differentiable on the open interval, and the endpoints outputs are equal, so Rolle's theorem applies. When I take the derivative, I get 2x plus 3, and we should be able to find a point within this interval such that the derivative is equal to 0. So if we solve the derivative equal to 0, we subtract 3 from both sides and divide by 2, and we get x is equal to negative 3 over 2, which is, in fact, the axis of symmetry. So if we go ahead and graph, that, you have a little parabola right here, and you have your minimum right there, and it's going to have a little bit of a horizontal, oops, I can't draw with my finger very good, but it has a horizontal tangent right here. Okay. Alright, if we look at another example here, we have this g of x function, which is equal to negative 3x times the square root of x plus 1. And we're going to consider it on the interval negative 1 to 0, closed interval. Negative 3x is a continuous function, and the square root of x plus 1 is also a continuous function. We are on the domain of the square root of x plus 1. Square root of x plus 1 is defined for x greater than or equal to negative 1. So we're okay there. We're continuous on that closed interval. However, it's going to be a little bit harder to determine if it's differentiable on the open interval. We can take the derivative of this, and we want to double check to make sure that it's okay on negative 1 to 0. We're not going to end up dividing by 0 or something like that. I'm going to rewrite it as a little bit more friendly to take the derivative, and you see that it is a product of two functions, and negative 3x, and then the square root of x plus 1, or we can write it as x plus 1 to the 1/2 power. Okay, so it's going to be derivative of the first, which would be negative 3 times the second function, plus the first function times the derivative of the second function. Okay, I'm going to do a little bit of algebra. I'm going to factor out a negative 3/2 because we have 3/2 in the second piece, and then we're going to factor out the x plus 1 to the negative 1/2. So that's going to happen is I get this 2 here. This 2's got to counter this divide by 2. So that's where that 2 comes from. Because originally this didn't have a divide by 2. So that's where we're going to do that to counteract that. And then x plus 1. And we get the x plus 1 there because the exponent here is 1. When I take away a negative 1/2 from 1/2, it's positive 1. Okay. And then we will rewrite that as negative 3/2, 3x plus 2 all over x plus 1. And I got to check, can I plug anything in from the open interval negative 1 to 0? And the answer is yes. The only place that I'm going to have problems is if we plug in negative 1, which is not included in the open interval, or anything less than negative 1, which is not included in the open interval negative 1 to 0. So it is differentiable on the open interval negative 1 to 0. The last thing to do is to check to make sure that the endpoints outputs are equal. So when I plug in negative 1 to the original g function, you have negative 3x times square root of x plus 1. Well, if we plug negative 1 in, that square root becomes square root of 0, and then square root of 0 is 0. So it's 0 for the first endpoint. If we plug in 0, the negative 3 times 0 is going to give us 0. So the endpoints are equal. It's continuous on the closed interval negative 1 to 0, and differentiable on the open interval negative 1 to 0. So Rolle's theorem does apply, and we can go ahead and set the derivative equal to 0, and So for that derivative there, in order for it to be equal to 0 is when the numerator is equal to 0. So when is 3x plus 2 equal to 0? Well, if we solve that, it would be negative 2/3. Okay, and we'll draw a little bit of a picture to see what this looks like. So negative 1, negative 2/3, so it's going to look roughly something like that. So again, we see that Rolle's theorem applies. It doesn't tell us how to exactly find it, but it just tells us there exists one. And then what we have to do is we have to do a little bit of algebra. Take the derivative, set it equal to 0, and then solve for x, and that will actually find us the value. All right, in this next example, you can easily see that it might be easy to get carried away with just going ahead and finding the derivative and checking the endpoints to see if they're equal to each other. But this one doesn't apply. If we plug in the endpoints negative 1 and 1, we're going to get 0 both times. However, the function is not defined at 0. And because 0 is in our interval negative 1 to 1, it's discontinuous on that interval. And you can see by the graph here, rough sketch, that on the interval negative 1 to 1, it doesn't look like we have any extrema. We don't have any places where we'll have a horizontal tangent. We do have a vertical tangent at x equals 0, but we don't have any horizontal tangents. So this shows that if we have discontinuity, then Rolle's theorem will not apply. I have one more example of doing Rolle's theorem, and then we'll get into the mean value theorem. All right, we'll look at one more example of Rolle's theorem, and then look for another video on using the mean value theorem. Those are the two things in 3.2 is Rolle's theorem and mean value theorem. The actual application in the problems won't be real difficult. You just need to make sure they meet the conditions of the theorem. The last one we're looking at is this k of x function, which is equal to cosine x, and we're going to look at it on the closed interval 0 to 2 pi. Cosine is certainly continuous on 0 to 2 pi, and it is also differentiable on the open interval 0 to 2 pi. And we know what its derivative is. It's negative sine. We need to check the endpoints. We need to check the endpoints to make sure the endpoints' outputs are not equal, and they're both equal to 1, so that's good. And so if we have three conditions, so Rolle's theorem applies, and we'll take the derivative and we get negative sine x. So the derivative is equal to 0 when sine x is equal to 0, and sine is equal to 0 when it's equal to an integer multiple of pi. So 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, negative 2 pi, negative 3 pi, etc. Well, the only one of the integer multiples of pi that fits in our interval 0 to 2 pi is, and I mean open interval, is just regular pi. And again, we have what it looks like, the cosine wave. You can see that it does have a horizontal tangent at pi there. So we have met the three conditions of or three hypotheses of Rolle's theorem, and so therefore our conclusion is we should have a horizontal tangent, which in fact we have observed.